Okay, so lecture 6, linear algebra and vector algebra, algebraic addition and scalar multiplication of vectors, geometric addition and scalar multiplication of vectors, and linear combinations. So we've introduced vectors as column matrices like this, and we want to talk about how you add them and multiply them. Adding and multiplying just algebraically is pretty easy. When you add two vectors, you just add the components. So 2 plus minus 5, minus 1 plus minus 2, 3 plus 6. And that's going to give you minus 3, 9. So adding is pretty easy. You just add the corresponding numbers. Multiplication is also pretty easy. We have v1 is 2 minus 1, 3. V2 is minus 5, minus 2, 6. So what is 2v1? 2 times v1 is 2 times 2 minus 1, 3. And then we multiply the 2 to each one of the entries, so we get 4 minus 2, 6. Minus 3 halves v2 is minus 3 halves times minus 5 minus 2, 6. And again, you multiply that to each one of the three entries, you get minus 15 halves at the top. Minus 2 times minus 3 halves, the minus cancels out, the 2's cancel out, so you're left with 3. Minus 3 halves times 2, you get 6 over 2 is 3 times a minus 3 gives you minus 9. So algebraically, if we're just dealing with numbers, it's pretty easy to multiply matrices, and it's pretty easy to multiply vectors by numbers and multiply by numbers and add them algebraically. So what do they mean geometrically? So geometrically, 2 dimensions is easy, 3 dimensions is hard, because it's always hard to draw in 3 dimensions. So in 2 dimensions, there's W1 and W2. How do we think of this? I'm going to think of the first number as being my x coordinate, the second number as being my y coordinate. If I draw these vectors, 1, 1, 2, there's the vector W1, the vector W2, minus 2, 2. There's the vector W2. So easy enough to draw. So I'm just going to write down what those vectors are, 1, 2, and minus 2, 2. So we don't have to go over. So what's W1 plus W2? Well, we know W1 plus W2 is equal to 1, 2, because that's W1 plus minus 2, 2. And if you actually add those together, 1 minus 2 is minus 1, you get 4. So that should be the vector we get. Geometrically, what we're doing is 1, 2, 1, 2, 1, 2, 3, 4. So W1 is 1 unit to the right and 2 units up. W2 is 2 units to the left and 2 units up. Like that. So W1 plus W2, if I take W1 is 1 unit to the right and 2 units up, and then W2 would be 2 units to the left, 1, 2, and 2 units up. So there's W1. W2 is technically has its origin at the, its tail as a vector at the origin, but if we slid that up to here, we get W2 up there. W2 is 2 units to the left and then 2 units up. W1 is 1 unit to the right and 2 units up, 1 unit to the right and 2 units up. And so that gives me there. So there's W2, W1. So the addition is that vector. So given any 2 vectors, we can draw this parallelogram whose sides are the opposite sides of the same length, W2, W2 in parallel, W1 and W1 in parallel, and this diagonal is the sum of the 2. So 2W1 and 2 minus 3 halves W2. Well, 2W1 is 2 times 1, 2 equals 2, 4. I always want to write them as fractions. Minus 3 halves W2 is minus 3 halves times minus 2, 2. That's what W2 is. And minus 3 halves times minus 2 is 3. Minus 3 halves times 2 is minus 3. So what does the sum of these things look like? I mean, not the sum, what do these products look like? Well, W1, 1, 1, 2 is like that. 2W1 is 2 units to the right and 4 units up. And it's on the same line that W1 had defined, right? It's just W1 stretched out by a factor of 2. Now, W2 is this vector, 1, 2, that is W2. Minus 3 halves is 3 minus 3, 2, 3, which is out here. It's minus 3 halves W2. So multiplying by minus 3 halves, what did we do? We stretched it out by a factor of 1.5, but the minus sign flipped the direction of it. This still lies on the same line of the other two. So a linear combination, and that's in a box, so it's a thing to remember. If we have a collection of vectors, a linear combination of vectors is any vector that's some constant times the first one, plus some constant times the second, plus some constant times the third, et cetera, et cetera, et cetera. So 2W1 minus 3 halves W2. This is a linear combination of W1 and W2 because it's a constant times W1 plus a constant times W2. The constant times W2 being minus 3 halves. So 2W1 minus 3 halves W2. We'll go back up here and see what 2W1 was. That was 2, 4. Plus, and minus 3 halves W2 was 3 minus 3. And so that becomes 5, 1 is the vector. So we started off with W1 being that vector, multiplying by 2, stretched it out so that it's a 2, 4. 1, 2. W2 starts out as this vector, multiplying by minus 3 halves. Stretch it out so it's this vector. So this is 2W1. W1 doubled, and this is minus 3 halves W2. And now we know what the addition should look like. If we draw minus 3 halves W2, this parallelogram, or 2W1 up there, they'll meet right there at 2W1 minus 3 halves W2. That's this vector right there. And so that's the addition of that. Okay, so I'm going to show you a little GeoGebra thing. If I can find it. Here we go. So here are 2 vectors in the plane, the black vector and the red vector. We can put in another point and a vector that goes to that point. Is this vector here, we'll bring it in a little bit, is this vector a linear combination of the red vector and the blue vector? Well, we can extend, I think this is going to be the red vector. Oh, we can extend the blue vector a little bit. Find a K1 that extends the blue vector. We can extend the red vector a little bit. And then if I take this black vector and move it to the tip of the red vector, nope, didn't want to do that. That gives me that. Or I can move the red vector to the tip of the new black vector. And so that gives me this blue vector D as a linear combination of the vector that goes to B and the vector that goes to C, multiply each one by a number that stretches it out a little bit, and then I can build my parallelogram and find D. And in fact, no matter where I move D around, I can always find an extension of the black vector B and the red vector C, so that those two extensions added together give me D. Okay. So we'll go back to the lecture, and that's it.